All right, it's 10 o'clock, so let's get started. So first and foremost, welcome to Reyes. My name is Orlando Ayala. I'm an associate professor at Old Dominion University, specifically in the Engineering Technology Department at Old Dominion University in the College of Engineering. I'll be talking to you about forces in static fluids today. But before that, I'm gonna give you a little bit more of the background of my expertise and so on. So first and foremost, the rules of engagements is very simple. Feel free to ask any question during my presentation. I'll be happy to stop at the moment you ask me question. I like to have this more as a live interaction rather than that boring interaction of me talking and talking and talking. So feel free to jump in and ask any question you might have at the moment. I'm touching upon some concepts. Some of the concepts you might be familiar with, some others might not. And if you have any doubt of any kind, just let me know. So perhaps you already know, but just to make sure you know where I am situated. I work at ODU. So where is ODU? ODU is located in the United States, specifically in the Commonwealth of Virginia, on this area that I just highlighted. In the Virginia, we are specifically at the southeast side of Virginia, right here in Norfolk, Virginia, in Norfolk and Virginia Beach, in that area, and we call that area the Hampton Roads area. Old Dominion University is right there in Norfolk, right here in Norfolk. It's very close to the water as well. Beautiful area, let me tell you. There are so many things going on in this area. And I can tell you that, for instance, we are next to the largest naval station. The naval station, the United States Naval Station, is right here in this area. It's the largest one in the world. Another very cool, interesting engineering side of note is that we have a Chesapeake Bay Bridge Tunnel, which is the largest tunnel in the world, if I'm not mistaken, by the way, because the technology has been grown and things have been moving so fast in the world that I don't even know whether it's the first one. But it used to be one of the 7th marvels of the world in engineering. So this is how it looks like my university, Old Dominion University. This is a beautiful campus. Look at in the back, there's water. My office is right behind these trees right here. So who am I? So like I said, I'm an associate professor at the Engineering Technology Department. I am a mechanical engineer by training. And what do I do here? I teach thermodynamics, heat transfer, fluid mechanics, and HVAC system. HVAC is heating, ventilation, and air conditioning systems. I'm part of the MET faculty, the Mechanical Engineering Technology faculty. And I'm proud to say that I'm also advisor of very nice groups, student organizations at Old Dominion University. One of them is the Makerspace, the other is Engineers Without Borders, and the Baja SAE. I'll tell you more about those three in a second. I have been blessed in my professional life to have been involved in so many areas of the application of engineering. I'm a faculty right now, so meaning that, of course, I'm dedicating my life to the academic side. But I used to work for the company. I used to work for a consulting company. I used to work in the industry, so I know exactly what goes on in the industry. I was trained as a mechanical engineer, did my master's degree, got my PhD as well in 2005, sorry. And I went to work for the industry for several reasons. And so I had the nice opportunity to be able to use what I learned in the industry. And when I teach my classes, that's what I do. I always try to bring to the class all the experiences I had in the industry. On the fluid mechanics side, I design things like the ones in the picture. That right there, you see a room full of pumps. And pumps are used to move fluids from one point to another. So everything you see there in that picture, although this is not my own project, we design. in my times working for the consulting company. One of the coolest projects I was involved with was a large swimming pool we were hired to design. So we work alongside architects, civil engineers, electrical engineers, and so on and so forth to design a large swimming pool, a very large swimming pool. The larger the swimming pool, the more mass of water you have to move around, the larger the pumps that you will require. So I was involved in designing a very large and beautiful swimming pool. I don't know whether it was built or not, but I designed the swimming pool. Um, on the thermodynamic side, I did not design things like you see in the picture. Many of you might not know what it is. I'll tell you in a second. But I didn't design that, but what I did was to evaluate its performance. That right there is a turbine. The same turbines we use in things like this, an airplane, the same turbine. But I did not study the turbine in an airplane. What I did study in a turbine in a power generation plant. So I look at the performance of that turbine to see how it was working, to detect any possible failure, any possible future failures, and so on and so forth. Because when equipment are about to fail, there are parameters that change. That if you read them ahead of the game, you could prevent the failure. Similarly, I also look into engines, but not the engines of the car. And by the way, the fact that I am a mechanical engineer, that doesn't make me capable of fixing my car. I don't know how to fix my car. I know how it works, but I don't know how to fix it. We need a mechanic for that. They know much better than I would know. I did not study the engine of a car, but I also reviewed the performance of an engine in a particular plant in this industry I was working on. Another side of the knowledge of the expertise that I have is heat transfer. And of course, many of you might have heard about the different heat transfer phenomena that occur. Those are conduction, convection, radiation. And we use that in common things in our house. In cooking, heat transfer is extremely important. But the one that I have dedicated a lot of my time is computing the heat that could go into a house during summertime, for instance. If it is summer, it's really hot outside, we want our house to be cool. And nature, because outside is hot, nature will put heat into the house because heat goes always from high temperature to low temperature, high temperature to low temperature. So this is where an air conditioning system will come into place to be able to remove that heat that Mother Nature puts in the house. So Mother Nature gives you heat inside the house, then we put an air conditioning system to remove the heat. So in my engineering in engineering practice, I have also designed system of these kinds, that the ones that you might have in your house. So anyway, those are the things in general what I've done in my life as a professional mechanical engineer. What have my students done? What do they do while going through their careers here at Old Dominion University? Well, I advise 3 students organizations that I'm so proud of them. One of them, Engineers Without Borders. The other one is the Baja Car Club, and the final, the Makerspace. Let me start with the Makerspace. Makerspace is, by the way, I'm broadcasting from the Makerspace, by the way, which we call the EMIC. In the Makerspace, we have a humongous, large space where we have many equipment that the students can use to fabricate, to create things. So the idea of the Makerspace for the students to come here, create their own ideas, come up with their own ideas, design those ideas, and make them. That's so the word maker space. So we have spaces we have, of course, 3D printing. We have in the metal area, we have the wood and composite area, we have the welding area, we have the electronics area. So we have any sort of equipment that any students could use for free to build their ideas, When it comes to the Baja Club, that's another club that they could come to the Makerspace to get things done. So Baja, what they do is to build almost from scratch that car that you see in the picture. That's our car from 3 years ago, because COVID it was in the middle. So 3 years ago, we built that car, and they have to build everything. Of course, they're not going to build the tires, but they have to select what tires are appropriate for the good performance. But the frame, the things like the tires, the rings, the engines are things that they have to just grab and use. But other than that, the the drivetrain, the frame, the brakes, all of that they have to design. And in some cases, they don't need to build everything from scratch. They just need to buy the right part for the design they came up with. And finally, let me talk about another really, really nice student organization, which is Engineers Without Borders. Engineers Without Borders is an organization that goes and help people around the world with problems that an engineer can fix. One example of that is that we are right now helping a poor community in Guatemala. That community does not have access, direct access to clean water in their houses. They have to walk about a mile, depending on where the house is. They could be walking like half a mile to 2 miles, depending on how far the house is from the source of the water. But they have to walk that every 2 days. So moms, our kids are walking and walking all those streets to bring the water to their houses. So what we're doing is designing a pump system that can take the water from that source and take it directly to their houses to improve their life. All right. So that's what we're doing around here, at least my students, with my advice. Before I go into the class, I just gave you my background, and now you know me a little bit better. Let me tell you something that I'm gonna come back every now and then as we go along into this class, and that is that engineers are designers and or inventors. We could be inventors and we design the invention. One thing is invent something, coming up with an idea, okay? The light bulb goes on. That's an idea that you need to design. So not only as engineers, we come up with that idea, but also we design that idea. We make it happen. And that's why we are designers and inventors, okay? Now, what is important to recognize here is the following. Scientists study how Mother Nature behaves, and they do come up with mathematical equations, mathematical models. That's their job. We as practitioners, engineering practitioners, we don't develop equations. What we do is to use those equations that those dudes, scientists, came up with. Whatever they come up with, whatever they learn from Mother Nature, we use that to our advantage because we want to fool Mother Nature through devices to improve our life. Like, for instance, the air conditioning system. A scientist found out, and by the way, the name of the scientist is Fourier, but a scientist many years ago, he found out that heat goes from high temperature to low temperature. And he developed some equations, by the way. He developed those equations to quantify that amount of heat. So what did we do as engineers? Okay, 100 years ago, a guy whose last name is Carrier came up with this device called air conditioning system. And what does air conditioning system does? The air conditioning system fools Mother Nature. Because with the AC, what we do is to take heat from a cold source to a hot source, which is the contrary to what Mother Nature would do. And we were able to do it because scientists many years ago found out that the heat goes from high temperature to low temperature. So we as engineers reversed that. Of course, that implies that we need to pay some amount of energy, of course. To be able to fool Mother Nature, we must use energy, definitely. So at the end, engineers use science, the science that somebody else came up with, and math to solve real world problems. Now, we could also become a scientist, let me tell you. We could also become scientists if we want to. And we have to, as engineers, we have to make a decision whether to go into the scientific side of things or the application side of things. There are many companies that do have departments, research and development departments. So if you go into a research and development department, then you are an engineer that goes more into the scientific side. So you could also come up with equations if you like. You could also spend your life studying Mother Nature. You could. Or you could go to an application, go to the industry just to solve problems, By the way, this whole thing of solving the problems is always based on engineering design process. And the engineering design process starts by defining the problem, plan solution. When you do plan solutions right here, right in these steps, that's when you use the knowledge that scientists came up with. Once you prepare a solution on paper, then you build, you make a model, then you test the model, and then you reflect and redesign that model. And by looking at the problems you found in that preliminary model, you create another problem. You define another problem, and once again, go and plan solutions. By the way, this whole engineering design process, that's what we want to happen in the makerspace. Oh, one thing that I forgot to mention about the makerspace, by the way, that space is run by the students, for the students. I'm the advisor, but they are the ones coming up with everything in this space. They are the ones deciding what to run, what to do, what not to do. Of course, they always are in contact with me to make sure everything is within certain constraints. Of course, that's as anything in life, right? So let's go into this class. Let's go into the class agenda. So the first thing I'm going to do is to talk about fluids and their properties. They're going to be very generic concept, of course. And this is the part that if you guys have any question whatsoever, please let me know. Please let me know. We're going to be talking about pressure, which is one property of fluids, and how pressure behaves in a static fluid. We're going to be talking about buoyancy force, following by the stability of those bodies that are submerged or floating. And finally, we're going to be talking about the difference between theoretical experimental work, collecting data, processing data, and homework. The last three items are related to the homework assignment that you might want to get involved or not. It's up to you. I'm going to give you access to that, to a virtual lab that we created here at Old Dominion University. And it's up to you whether you want to continue with the homework assignment. I think it's a great experience if you go through that. We won't have the time to cover that today. You got to do it after the class. But again, I really encourage you to do so. I'm going to give you at the end of the talk, I'm going to give you also my email. So if you have any question on that lab, if you decide to go for the lab, I'll be happy to address any question you might have. At the end of the day, what I'm doing today with you is to get you involved in typical activities college students are involved in. So I want you to see what is it that the students do here through my classes, for instance. Okay. Now let's start with fluids and their properties. First and foremost, the basic comes. So I'm going to read a very fancy definition of what a fluid is. Very fancy. Okay. And it might not make sense to you, and that is fine if it doesn't make sense to you. But that's the original, the base definition of what a fluid is. And that is a substance that continually deforms or flows under an applied shear stress, regardless of the magnitude of the applied shear stress. Now, I highlighted shear stress because that's a very fancy word, among many others in that concept, by the way. But shear stress is nothing that you could think about. Shear stress about just if you grab your hands and you put one hand after the other and you rub one hand against each other, all right? You start feeling the heat. If you start moving your hands, you feel the heat in the palm of your hands. Well, that heat comes because of friction, and that friction comes because of a shear force. That's shear stress. That parallel motion that you see, that you feel in your hands, that's what we call shear and force or shear stress. Okay, so that kind of motion that is parallel to your hands, that's the type of motion that makes the fluid to deform. And if deform, it moves like in the pictures that you in the little videos that I have in my presentation right there. So a fluid could be a liquid or a gas. All right. But in this class, we're gonna focus only in liquids, only in liquids. I'm not gonna be talking about air. I'll be just focused in liquids. That's all. And let's start with this very important concept in fluid, which is pressure. So it happens to be that this guy, Pascal, in 1653, he came up with this relationship between force, pressure, and area. You might not know what pressure is, and that is fine, but you know what force is, okay? At this point, you know what force is. And area, you also know what area is right now. Well, happens to be that if I take if I divide force by area, that gives me pressure. And Pascal was the guy to find that in 1653. In 1663, he published his work, but he found this expression in 1653. As you could see, a long, long, long time ago. But such a powerful equation. He was studying modern nature and he found that equation, and happens to be that we use that equation in engineering a lot. But what is pressure? Well, pressure is more related to the molecular motion, how molecules behave. So pressure is related to how fast those molecules collide among each other. How fast those molecules hit the walls. The faster they hit the walls, the higher the pressure. Because think about this. Think about this. The molecules hitting the palm of your hand. The faster they hit your hand, the more you're going to feel something in your hand, right? Let me give an example. I'm pretty sure you've seen that. Not a kid running away. Well, you might have seen a kid running away, but you have seen a syringe. Well, I am sure that many of you, if not all of you, I am sure that many of you have put a finger in the tip of the syringe. And I'm sure you've tried to move the plunger. I'm sure you tried to move the plunger. And you know what happens. You know that you start feeling something in the tip of your finger. So what are you doing? Let me go back to this video, by the way, because I want to say one more thing about this. If I want to increase the amount of collisions of those molecules against a wall, there are two best ways to do so. One, increase the temperature of that volume. If I increase the temperature of that volume, the molecules will move faster. The molecules will move faster, and by moving them faster, I'm going to get a lot more collisions. But the other way, which is the one that I need you to remember for this class, is by reducing the volume. If somehow I reduce that volume to 1/4 of it, keeping the same amount of molecules, by the way, I keep the same amount of molecules. If I reduce that area, I'm forcing the molecules to move shorter distances. And if they move shorter distances, they must collide a lot faster. So that's why reducing the volume will create more pressure. And going back to this idea of the syringe, when you put your fingers on the tip of the syringe and you move the plunger against your finger, you are trying to reduce the volume of air. And when you reduce the volume of air, knowing that you have the same molecules inside, the molecules will tend to hit your finger faster. And that's related to high pressure. So please write this equation down. Please write this equation down. I'm going to give you 5 seconds to go, 10 seconds actually, to go and grab a piece of paper and a pen. Please go ahead, grab a piece of paper and a pen or a pencil and write this equation down. That equation that Pascal found for us 400, 500 years ago, a long time ago. And since he developed that equation, engineers start using that equation for things that you'll see as we move on in this class. So once again, write this equation down. Pressure is equal to force divided by area. One more property about pressure is that since it's related to how molecules hit the wall, a full hit will be if the molecules are hitting perpendicular to that area. So the net direction of the fluid pressure or pressure force will be always perpendicular to the area. That's another property of pressure. Now, with that said, now that we know what pressure is, let's move on into two more concepts that I'm going to need during this class. And they are density. Perhaps some of you have heard that already. If not, then that's a number that gives me a sense of how heavy, no, not heavy, how much matter I have in a particular volume. So density, the equation of density is defined as mass divided by volume, which will tell me how much mass I have in a particular volume. And then related to weight, sorry, related to density, I have the weight. So weight, which is something related to gravity on Earth, right? Weight is nothing but mass times gravity. Weight is equal to mass times gravity. And weight is another form of force. And keep in mind that pressure is related to force. Remember, pressure is equal to force divided by area, meaning that if I have a force applied to a fluid, I have a pressure. Also, that means that if I have a pressure in a fluid, I have a force, or I can use a force, okay? So wherever you see force in a fluid, there must be a pressure. Wherever you see pressure, there must be a force in a fluid, or a force that you could use from the fluid. So that's one form of force. And here's another one, which is weight, another form of force due to the gravity, due to the fact that we live on Earth, and Earth is trying to pull all matter into its center. That's what gravity is. All right. Now notice that density has mass right here, and that I have weight. That in the weight I also have mass. Well, if I get the mass out of this equation, that'll be density times volume. I plug it in here, and I finally get that weight is also equal to density of the fluid, gravity times volume. And please, my friends, write these equations down, because we're going to need them for something later on. And see, what am I doing with you? I'm manipulating equation. Remember, what do we do as engineers? We use science and math. So on this part of my class, I'm dealing with the math. And it's not a big deal. It's not a humongous amount of math that we need to deal with. Just hang in there. It might be boring at times, but we're going to get into very interesting results. I promise you that. So hang in there, and let's keep taking a look at these equations. Now that we know what pressure is, and you wrote this equation, let me give you a few more seconds to write this equation. So write the equation for pressure, which is pressure, or P, is equal to F divided by area, by A, force divided by area. Then density is equal to mass divided by volume. Then weight is equal to mass times gravity, or is also equal to density gravity times volume. So now that we know those very simple, those properties, those are not the only properties of fluid, but those are the properties that I'm interested in introducing to you today. Let's talk about pressure. How does pressure behave in a static fluid? We know what pressure is, but let's see how that behaves in a static fluid. And why might I be interested on that? Because I might be hired to design an aquarium. Listen, I need to know the pressure so I can compute the force that the water is exerting against the glass in that aquarium. And I need to know the force. Why? Because if I don't know, that glass could break. I know that if I put a very thin glass, that glass is gonna break. It could break. Sorry, I'm not gonna say will. It could break. So if I know the force produced by the pressure of the fluid, I can decide and design the thickness of the glass. So that's why it's so important. And see, once again, it comes from a concept that Pascal developed 500 years ago. From that relationship. So we could use that relationship to be able to design an aquarium. Once again, engineers use concepts that scientists came up with. Now, Let's see how that behaves. And you know the importance of that pressure, why it's important to look into that. But let's see how pressure behaves in a static fluid. So many of you, if not all, have been at the bottom of a swimming pool. You have dived into a swimming pool. And if you go to the bottom of the swimming pool, depending on the depth of the water, you might even feel a kind of a noise in your ears. And you always say, oh, it's due to pressure, the pressure of the water. Well, I want to get with you into that phenomenon of the pressure of the water. So the question is, can we compute the force at the bottom of the swimming pool? And the answer is yes, we can do that. How can we do that? Well, let's say I'm floating on the surface of the water. If I'm floating on the surface of the waters, I don't feel any force. But as soon as I go to the bottom, I feel a force. So if there is a difference between me floating and me being submerged at the bottom, that difference has to be due to that mass of water. Because the only difference between me being at the surface at the bottom is the water. It is just the water. So if you keep thinking, if it is the water, then that force must be related to the weight of the water. So force, the force that I'm feeling, or the force that the bottom floor of the swimming pool feels is equal to the weight of the water. Okay, now this is what I need you to do. Go back to the 3 equations that I told you to write down and look at the equation for weight, the second one. What am I going to do? I'm going to plug in that equation into the W we have in this relationship I just found. So weight is equal to density times gravity times volume. Okay. But see, look at this. So density is the density of the water. There's nothing like I change. I know it's water, so all I need to do is to go to a table and read that value. And gravity is gravity due to the fact that we live on Earth. Okay. But volume, I need to find another equation for volume. What's the volume of that swimming pool? Well, that volume of the swimming pool is related to the area of the bottom surface and the height of the water. And volume in this case is nothing but the multiplication of that area times the height. That's volume. That's that volume. Now, look what I'm about to do. I'm going to move this area right here to the left-hand side. Since it's multiplying on this side, it's going to go to the other side dividing. And this is what I get. Force divided by area is equal to density, gravity, and height, the height of the water. Here's what I need you to do. Go back to the equations I told you to please write down. And you're going to find one equation that has force divided by area.
Professor, we have a couple of questions.
Oh, really? Cool. So shoot them out. What do we have?
So from Jackson Shelton, we have the pressure of the fluid is the force applied to all sides of a container, correct?
That's correct. That's correct, Jackson. That is totally correct. Now, the magnitude of those forces will depend on the area, and it would also depend on what side you're referring to. Because the bottom side, like in this case in the swimming pool, is different to the ones on the lateral wall. And the lateral walls discussion is a little bit more involved, which I prefer to leave to another class. But yes, you're right. You're totally right. The answer is yes.
And then from Kelly Ferguson, we have, is force always equal to weight?
No, it's not always equal to weight. But in many cases, specifically for static of fluids, that's the case. But not always. It's not always like that. It depends. It depends on the case. In this case, it works, but it's not always like that. Like I said, especially if the fluid is moving. If it is moving, then other kind of forces show up. Any other question, Tyler?
We have one asking about as we decrease volume and pressure is increased, is it related to the ideal gas law?
Yes, definitely. But what happens And who was this person?
It was an anonymous.
An anonymous. Okay, that's fine. So whoever built that equation, yes, is related to that. But amazingly, that ideal gas law, that behavior of the ideal gas law also applied to a liquid. If you somehow, look, what happens is in a liquid, it's very hard to change the volume, but it's possible. It's not impossible. So if you do so, you are increasing pressure. So yes, it applies to ideal gas, but it also applies to any gas. And even a liquid. It's very hard to get it accomplished for a liquid, but it's even true for a liquid. So anyway, keep asking questions. Tyler will always tell me at any time when there are questions around. Good questions, by the way. Very good question. So going back to these equations for the force divided by area, you have another equation. Well, you see that there is force divided by area, and that is pressure. That is pressure. Okay, so look at that equation. That equation is telling us how pressure behaves in a liquid. And it's telling us that I can increase pressure by increasing density. That means by using, instead of water, something heavier, another fluid that is heavier than water, like mercury. If I had a swimming pool made of mercury, then the pressure will be larger. I can also change pressure by changing gravity, but we live on Earth. We only have one gravity, okay? But if I go to Mars, the pressure in Mars, because it's a bigger planet, the gravity in Mars is larger than the gravity on Earth. So if I go to Mars, then the pressure will be higher. But since we live on Earth, at least for now, who knows? Maybe one of you will be living in Mars in a few years. Who knows? But since we live on Earth, that gravity is just a number. It's a constant. And then the variable h. That h is the height, meaning that the deeper you go into the swimming pool, the larger the pressure. So pressure increases as you move down. Notice the following: pressure increases as you move down in the liquid in the gravity direction. As you move down in the gravity direction, the pressure in a liquid increases. It's true. It is true. And as you move up, the pressure in the liquid reduces. So important. If you move up, you are decreasing pressure. If you move down, you're increasing the pressure. And let me give you an example. Let's see whether you got this concept. So if I try to compare the pressure of B and the pressure of A, those 2 points in that example, I have to say that the pressure at B is larger than the pressure at A. And I know the difference, because the difference will be the density of oil times gravity times 3 meters. The pressure at B is larger than the pressure at A by density of oil, gravity times 3 meters. And if I keep moving down, let's say to point C, then it's even larger. Once again, as I move down, pressure increases, and if I move up, pressure decreases. And please note that pressure depends only on a distance measured in the gravity direction. You don't see in that equation any variable that depends on the horizontal direction. H is always vertical in the gravity direction. That means that if I move horizontally in a liquid, the pressure does not change. And that is true. The equation is telling me that, and people have measured that in a lab, and people have found that it is indeed true. If I move horizontally, nothing changes. So B and D must have the same pressure.
We have a couple more questions, Professor.
Cool, even better. Shoot them out.
All right. So from Jackson Shelton, we have, so pressure is only dependent on how deep you are in a fluid, not necessarily how large the body of the liquid is.
Oh yeah, Jackson, totally true. You got the point. Yes, sir. It doesn't depend on the how big it is. It only depends on the vertical direction. That's it. It could be a lake, or it could be a cup of water. If they have the same height, you will have the same pressure. Yes, it's true.
All right. Excuse me if I get this name wrong, but Ahmed Mikawe, um, pressure increases while moving down. Does that mean temperature increases while moving down?
No. This is only, this is what I just explained to you is assuming that the temperature is uniform everywhere. That's a good question. I forgot to mention that in this class we'll be dealing only with constant temperature. If you include the temperature effect, what's going to happen is that the density will be affected. But without going any further, because I don't want to deviate from the concepts that I wanted to teach you today. No, temperature is not playing a role here. It's going to be constant temperature, and no, in a liquid that doesn't change. In a liquid that does not change, the temperature remains the same.
Okay. It looks like this next one is just a confirmation of the topic, but excuse me if I get this name wrong, Syed Gul. The pressure increases as you move down because it'll be the pressure of the water plus the atmospheric pressure.
Yeah, exactly.
Okay.
Yeah, you got it right. Exactly right. And it's pressure of the water. You might want, perhaps you were referring also to weight. It's true. It's all related. It's all related. Yes, it's true.
And then the last one, Malin Ranjan. Apologize if I got that incorrect. What would the unit of pressure be for this equation?
It depends on the units you use for density, gravity, and height. It depends on that. So if I'm using, the typical international system of unit, that pressure will be in Pascal. The same dude I told you about before, right? Pascal. He was the one to define what pressure is for the first time, 400 to 500 years ago. If I'm using the English units, there are two ways of presenting pressure. That'll be one in pounds per feet square. That's one way of presenting them in the industry, and another way is pounds per square inch. And if you do have that form of pounds per square inch, they call it PSI. P standing for pound, S standing for square, I standing from inch. So PSI, and you might hear many engineers telling you PSI, 400 PSI, 500 PSI. That's the typical jargon in the industry. Good questions. Good question. So as I was saying before, that and even confirming through the questions I got from some of you, the pressure only increases if you move vertically. If you move horizontally, it doesn't change. That means that pressure at B and pressure at D are the same, and they are the same. They are the same. But if you agree with me on that, then you must agree with me that the pressure at A and the pressure at E are also the same, and they are indeed the same. It's amazing, but it is the same. They are the same. Those two pressures are the same because they are located at the same height. Now, if I go to F, F must be a pressure lower than the pressure at E. Because remember, pressure increases if I move down, but pressure decreases if I move up. So if I'm at E and I keep moving up, the pressure at F must be lower, meaning that the pressure of this trap air, is lower than the pressure at A, which could be atmospheric pressure. And you know this phenomenon because all of you, if not all, many of you have drank soda from a cup using a straw. So what are you doing from the fluid mechanics perspective when you do drink soda with a straw? what you're doing is creating a lower pressure in your mouth, also known as sucking. When you say suck, what you're doing is creating a pressure in your mouth that is lower than the pressure in the ambient. And that pressure differential makes the fluid to move towards your mouth. That's it. That's all you're doing, lowering the pressure in your mouth. And please write this other equation down because it's very important for the next session. So pressure behave with density times gravity times elevation, okay? So with that said, let me get into the force that I wanted to talk to you about. So half an hour talking to you about background. Finally, we're here. Let's talk about buoyancy force and the stability of objects that are feeling a buoyant force, okay? Why is that important? Because buoyancy force are the ones that keep our boat floating. So if as an engineer, if I want to design a boat that floats without sinking, without failing, then I must know about buoyancy force. And you guessed it. If I spend a whole lot of time talking about pressure, it means that buoyancy is related to that. And let me prove that to you. Let's derive the equation of buoyancy. So notice if I have an object, which conveniently I assume I used a square object, a cube. And that's just for convenience. I could have done it with any other shape, but just for convenience, I'm using a cube. Now, what happens is that the cube will feel a pressure at the bottom that is larger than the pressure at the top. Why do I know that? Because pressure depends on density, gravity times elevation. And I know that the deeper I go, the larger the pressure. So I have a high pressure at the bottom and I have a lower pressure at the bottom. And since I know, because of Pascal, since I know that pressure is equal to force divided by area, I know that the pressure below produces a force larger than the force at the top or above. And that's what I do. So I have that the net force is equal to the force at the bottom minus the force at the top. And those forces are due to pressure. Now let's remember that pressure is equal to density, gravity, density times gravity times height. And if I plug that in, this is the equation I get. See, all I'm doing is plugging this P into this P. Yes, mathematical manipulation, but that's part of our job as engineers. So if I common factor density and gravity, this is what I get. Okay. So notice that the terms that I have between parentheses is the volume, the first term, H below times area. H below times area is nothing but the volume above the lower surface, this volume here. Look at this. This volume, this blue volume. And H above times area is another volume, and that is the volume above this volume right here. And since I'm subtracting one with the other, the net volume I get is this. And that is the volume of the object. That is the volume of the object. This is what I get. See, look at that. Buoyancy force is equal to density, gravity times volume. At this point, I want you to look at the equation of density of weight that I asked you to write down. Please take a look at the equation for weight that I asked you to write down. So I'm sure you just noticed that it's pretty much the same equation, but I can tell you that no, they're different. They look the same, but they're not the same. What's the difference? The difference is the density, because for the buoyancy force, the density is the density of the fluid surrounding the object. For weight, the density is the density of the object. Okay? So the density is key, and also could be the volume. And let's talk about that in a second.
We have a couple of questions, Professor.
All right, go ahead, Tyler. Tell me.
So the first one is from Said Gould. My question is, what if there is a pool in space, like it's in the International Space Station? What would the pressure be for that pool?
That's a great question. Can you imagine if they get a swimming pool there? So what happens is that since there is no gravity, the pressure does not change. That's a great question. That's a great question. If I had a swimming pool in the International Space Station, the density in the body of the water will be the same. Pressure does not change. Great, great question. Impossible to make a swimming pool there, but it's true.
And then it looks like we have another one after this, but from, let's see, Zane Muthupi, I apologize if I got that incorrect. Is the buoyancy force the same as upthrust?
I don't know. I don't know what's upthrust. If you could tell me if it is the lift, like in the airplanes, to make airplanes to fly. No, it's not the same. No, it's not the same. And they are the same in the sense that they are pointing in the gravity direction, but no, they're not the same. They're not the same. But if you could clarify what upthrust is, it'll be great. So I can clarify it even further.
And then the last one from Jackson Shelton is, so according to this relationship, the density of the object must be less than the density of the surrounding fluid for it to float?
Heck yes, of course, Jackson. Yes, if you want it to float, it has to be lower, the less, exactly. And I'm going to give you an example in a few minutes, though. So just to emphasize what you just said.
And we'll actually have a couple more. So from Kamaya Ranjan, apologize if I got that incorrect. Could you explain the difference between the two equations again?
Oh, yeah. I can go over that in a second. Are there any other questions?
Yes, and from Ali Yacob, apologize if I got that incorrect. Is it related to Archimedes' force or something like that?
Oh, yeah. This is Archimedes. Yes, it is. Yes, it is.
Right.
Yes, it is.
And looks like that is it. Yep.
Okay, good. So let's go back to the difference between those two equations. So the main difference is that even though they look alike, there are two main differences. One, for the buoyancy force, the density is the density of the fluid. For the weight, the density is the density of the object. Once again, the main difference is that for buoyancy, for the equation of buoyancy, this density is the density of the fluid. Whereas when computing weight, the density is the density of the object. Those are two different materials. Okay. There could be another difference. There could be another difference, and I'm gonna go back to that, but I'm gonna make it clear that there could be, and that is related to the volume. If the object is fully submerged, then those two volumes are the same. The volumes right here, boom, this one and this one. If it is fully submerged, those volumes are the same. But if the object is not fully submerged, then the volume is what we call displaced volume, and we call it BD. And I'm gonna get into that in a second. And then this volume is the volume of the full object. So those are the difference. Now, there was a question about Archimedes. Tyler, yes, you were gonna say something.
Yes, we just had one of our participants ask, what does the subscript B for V in the equation for FB stand for?
Displaced.
Okay.
That stands for displaced volume. That's displaced volume, because again, they could be the same or not. I'm gonna get into an example in a second. They could be the same or not. So Archimedes, interesting. See, so you saw the whole mathematical derivation we went through, right? You saw this, and it is all based on Pascal. But Archimedes already found this, and he found this in 246 before Christ. So even before Pascal, remember, Pascal found the pressure relationship in 1653. But many years prior to Pascal, Archimedes already found this concept of buoyancy. But he didn't know back in the day that it was related to pressure. He did not know that. We now know. He discovered that and he said, and this is an extract from what he wrote. By the way, the picture you see here is a picture of the original write-up that he put together on floating bodies. And he wrote, any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the displaced fluid. And if you see this definition, is nothing but the equation we just derived mathematically. That the buoyancy force is equal to the weight of the displaced volume. This right here is the weight of the displaced volume. Archimedes found that years prior to Pascal. He had no idea why that happened, but he was a smart scientist that studied modern nature and came up with an equation for us to use. And we still use nowadays. Notice, he wrote that equation 246 before Christ, and we still use it. What we did with Pascal knowledge is to learn why that happened. But still the same equation. And let me give you an example about buoyancy, which is related to one of the questions I got. And that is, again, the buoyancy force depends on the density of the fluid, and the weight depends on the density of the object, of the body. Okay? Now, we all have done what the ladies in these pictures are doing. What is it? Submerging a balloon full of air. You all have done that. Well, if not all of you, many of you have done that. You have grabbed your balloon, went to the swimming pool, and put it down. You submerge the balloon. And you all know what happens. Yes, this is what happens. So why did that happen? Well, let's look at the equations. When I was holding that balloon, under the water, there was a buoyancy force equals to density of the water times gravity times the volume of the balloon, or the ball, or the beach ball. And the weight of that balloon is equal to the density, but mostly the density of that balloon is mostly, the material of that balloon is mostly air. So this is density of air, basically, times gravity, times the same volume. Which one is larger? Well, the density of the air is about 1 kilograms per cubic meter. And the density of the water is 1,000 kilograms per cubic meter. So when you were holding in a force that is 3 times larger than the weight of the actual balloon or beach ball. So because I had a buoyancy force pointing upward, that balloon shoots up and goes up. But you know that at some point, that balloon will return to the water, and at some point it's gonna float. At some point it's gonna float. If you don't touch it and you leave it alone, you know it's gonna come back, it's gonna move a little up and down, and then stay stationary at some point. When that happens is because the buoyancy force is equal to the weight. So the water is just pushing the ball up, and the weight is countering that force. And because they are equal, the ball remains stationary. Now, why did it happen? Well, because Mother Nature is so smart. Mother Nature is so smart. When that happens is that the Mother Nature adjusts how much of the object must be submerged in such a way that that happens. So this displaced volume is the key. That displaced volume is what keeps the ball or whatever object floating. Because at the end, the only way for that ball to be stationary is for the buoyancy force to be equal to the weight. Now, let's get into the stability and get very quickly into the lab so I can give you time to run into the virtual lab that we prepared for you guys. So let's run for stability. But the stability is related to certain points that we define. And as we have buoyancy force, we need to know where that buoyancy force is located, where that buoyancy force is pushing. What's the central point of that? The central point, we call it center of buoyancy, and it's nothing but the centroid of the displaced volume. So the centroid is kind of, if you don't know what a centroid is, it's basically the middle of an object, all right? It's kind of the middle of the object to give you a sense of what that is. So if I have a cube submerged, then the centroid will be the middle of the object, the middle of the cube, right there in the middle, right there in the middle. Now, the center of buoyancy might be or might not be the center of mass. So the center of mass or center of gravity. So be careful. So the center of buoyancy is located on the centroid of the displaced volume, whereas the center of gravity is located at the centroid of the whole volume, the whole object. When is a submerged body stable? It is stable as long as the center of gravity is below to the center of buoyancy. See, what happens is the following. Why do we want that to happen? Because the buoyancy force points upward. So the buoyancy force will be pointing upward here. Let me see if I can do some drawing. Oh, sorry. It's pointing upward at this point, whereas the center of gravity is pointing, the gravity force, which is the weight, is pointing downward. The advantage of knowing that is that if the submarine tilts, goes sideways, there is a moment that will try to get the submarine aligned again. Why? Because once again, the buoyancy force points upward right here, and the weight points downward in this point. And by having those two located that way, if the submarine tilts, then it will try to go back to its original position. So that is an stable body. If it would not work like that, then the moment that what I call the right couple, it would be the other way around, and it will make the submarine to turn and turn and turn without stop. So when we build submarines or boats in general, you want to put most of the weight at the bottom, always. Most of the weight at the bottom, always. So that is if it is fully submerged. When it is floating, things change a little bit. So when it is floating, the relationship is no longer what we told you before. So now the center of gravity, instead of being below the center of buoyancy, it must be below to what now we're gonna call the meta-center point. So we have to look into this meta-center, and the meta-center is a fictitious point, doesn't exist. It's a fictitious point that we use as engineers as a reference, because we know that the center of gravity must be lower than the meta-center.
Professor, we have a question.
Okay, go ahead.
From Jesus Vivas, how can you find the centroid of an irregular object?
That's a great question, my friend, and it takes some work. All I can tell you, you have to go into integrals. to do that. Or you could decompose the irregular shape into a small regular ones, and we have equations that can help you to compute that. But yes, it's totally doable. It just involves some math, unfortunately. And I say unfortunately because I know many of you might not love math. And let me tell you one thing about math. It's not like I love math, but I learned how to get along with it because I love engineering. I love so much engineering that I decided to make peace with math. I don't love it, but I can get along with it very well because I know it works to my advantage. And at the end of the day, when you come to college, the truth is that we give you a lot of math that you might or might not use. If you go to a research and development office department, or you go to a very important national lab, then you need to be prepared for heavy math. That's for sure. But if you go to a company that they just want to improve their processes, then you don't need that heavy weight of math. The problem is that we don't know where you're going, and you might not even know where you're going when you're a student. When you're a student, you're getting ready for what's coming next, but you don't know where you're going. You might go to a research and development. You might not. You might go to NASA. If you go to NASA, you need the math. You need it. But if you go to work for a company that makes some, I don't know, soap, so you might not need it. You might not need it. But again, we train you for whatever comes to you, whatever that is.
We have another question.
Oh, really? All right.
Mhm.
What is it?
From Vincent Sturhan. Can the center of buoyancy be outside the volume of an object? And then in parentheses, he said, for example, a torus.
No, it cannot. Oh, yes. You know what? I'm glad you gave an example because the answer to that is yes. Yes, it could be outside. If it is a torus, yes, it could be outside. You're right. Good question. Definitely it could be outside. Definitely could. My intuition, my brain intuitively answered to you right away, no. But then after your example, no, it has to be outside. Yes, it has to be outside, and it is outside. It is definitely outside. And in that case, in the center of the torus. Good question. Good question, and thank you for opening my mind. I didn't think about it, but yes, it could be outside, definitely. Let's see, what else do we have? Okay, if it is floating, we're not comparing where the center of gravity is with respect to the center of buoyancy, but rather with respect to the metacenter. Now, the metacenter is a fictitious point. And by the way, the lab that you're gonna run into is a lab that will teach you how we do measure metacenter. And what I want you to do in the lab is to get the metacenter experimentally and compare that value to the metacenter. The equation I'm gonna provide to you is, I'm about to provide the how to obtain the location. And to get the location, getting into that, the location is by measuring the distance MB, this MB right here. And MB is equal to the moment of inertia divided by the displaced volume, the same displaced volume we discussed before to compute buoyancy. Moment of inertia, for those of you that do not know what moment of inertia is a property of an object that tells you how easy the object would like to be turned, okay? Would like to turn around, okay? How easy it is to turn. The bigger the objects are, the harder they are to turn. The smaller they are, the easy they are to make them turn. So the moment of inertia is just a fancy term to give us an idea on how easy an object could be, how easy it could be to turn an object, to make it turn away, to turn around. All right. But anyway, same reasoning as before. What happened is that the buoyancy force is aligned to the metacenter, and the center of gravity, the weight is aligned to the center of gravity. So we must have the center of gravity below, always below. And notice that in both cases, floating bodies or submerged body, we want the center of gravity to be the lowest possible, the lowest possible. And you always keep in mind, if you are designing a boat, That's what you always want to do. Now, I just told you that I want you to, what I'm gonna get into in explaining to you what you're gonna be doing in that virtual lab that we put together for you guys. And that is, where I want you to compare experimental work and theoretical work. But what's the difference between those two? In the theoretical work, this is pure mathematics, basically what we did today. Okay, so I'm just basically right now I'm wrapping up for you to let you go and work on the lab. And experimental work is in the laboratory. Another difference is that we predict magnitudes based on a model, based on equations. In the laboratory, we do measure those magnitudes, and the magnitudes do depend on the specific case that you're working on. And here in this class, I want you to calculate the location of the meta center of an object I'm going to show you. And I want you to determine that experimentally so we can compare them against each other. So in general, in the labs, we confirm theories or equations that we use to design things. So even though I want you to work on something not related to a design, I want you to prove that the theory works. But it is important for us as engineers that to certify that the theory works. Because if the theory do not work, then we cannot use the theoretical equations to design anything. We cannot, we should not. So what are we gonna do? We're gonna collect and process data. So you're gonna be facing this floating vessel that it has a weird shape. But the important thing is that the base is just a kind of a square shape, okay? And on top of that, we have this device that we make it just to be able to move what we're gonna be calling the movable object. This right here is a movable object that we're gonna start moving around to take some measurements, okay? Now, the experiment that you're gonna run into is gonna provide you data that would allow you to compute the meta center. And in the slides here, I give you a precise instruction on how to use the experimental data to get the meta center location. The data will be obtained at different locations of the movable weight that I told you before. And your primary purpose of the lab is to collect data, to collect the corresponding data. And by going through the videos, you're gonna be grabbing those values. The data, then you're gonna use that data to introduce it into an Excel spreadsheet that I put together for you to use. And Tyler, yes, is there any other question?
Yeah, we have a couple. So from Esha, is the meta center related to the center of inertia?
It is related because at the end, center of inertia is also related to the moment of inertia. So yes, I would say that they are related, definitely. Because once again, that meta center is related to moment of inertia. The moment of inertia is a term that tells you how easy an object can turn. And the turning is always around the center of inertia. So yes, they are related.
Okay, and then from Callie Ferguson, what does MB stand for again?
MB is just a distance, and it's a distance from the center of gravity to the meta center. And once again, I want you to, I like to remind you that the meta center is a fictitious point, okay? All right, so let's get into this. The results are gonna be presented in both numerical and graphical format. So please use the Excel spreadsheet. And if you do have any question, please feel free to ask me. So what are you gonna do? You're gonna collect data, and the data is the total mass of the floating assembly. When you go through the video, in the virtual lab, you're gonna be given that information. So pay attention to the video and start grabbing all the information that you need. So you're gonna need the total mass of the floating assembly. You're gonna need the weight of the movable weight, which is this guy here. You're gonna need the breadth or the width of the pontoon, and the pontoon is this is the whole thing called pontoon. And then you're gonna need the length, which is the distance into the picture here. You're gonna also be collecting data to fill in the tables here. Look at the bottom. This is the spreadsheet I'm gonna provide to you. What I want you to do as you move along into the video, start collecting the data, start collecting those angles and distances as you start and put it in this table. All right. So fill in the first table, which is the first table is moving the object in this slot. So you move this weight left and right, and as you move in this weight left and right in this slot, you're gonna be reading angles and you're gonna be reading distances. Like in this case, the distance is 75 millimeters. So you're gonna collect the data and plug it into the table. Then you're gonna fill out this second table, which is when the weight is on the second slot. And finally, this one when the weight is right at the, actually, the first table is right here, this slot. The second table is for this slot. And the third table is right here for this slot, right at the top. So we're gonna just measure 3 slots in the video. Now with the data, you're gonna produce curve of this kind, which are already automatically created in the spreadsheet. And the spreadsheet will automatically give you 3 values right here that I'm hiding from you so you can read them on your own. So you're gonna read those values next to the lines, and you're gonna use those values for the following process. So you compute the distance by following this step by step. You first compute the displaced volume, you then compute the center of buoyancy, and the equations I'm using right here are basically the equations I provide to you during the class. Then you compute the MB. Now, for the MB, that distance, experimentally, the equation is totally different, unrelated to what I taught in the class. In the class, I taught you the theoretical equation. Experimentally, there is some trick that needs to be done. Okay, there are some tricks that needs to be done. I'm skipping those tricks and just providing to you the equation that you use to be able to get MB with experimental data. So after you get the result from Excel, you're gonna use those values, plug them in here, and see what value of MB you get for the different location of the movable weight. And then finally, I want you to compute the theoretical work, and this is just the equations that I taught you half an hour ago. And your goal will be to compare the MB values you get out of the equation in the previous slide to the equation on this slide. The equation on this slide are the theoretical equations. The ones on the previous slide are the experimental ones. I want you to compare all those values against this one. And the question that I want you to answer is whether they are the same or whether they're similar. And what can you comment? If they're the same, are you happy with them? If they are similar, would you be happy? If they're just similar? So those are the questions that I want you to answer. And to get into that, we're gonna use a Blackboard system. Let me paste this on the chat group. Let me, where is it? Here we go. Let me paste this in the chat so everybody can access them. Where is the chat? Right here. So we don't have a chat room right here. Oh yeah, we do, sorry. So to all the attendees, here we go. This is the link. So all of you should have access to the link. And let me get a new chair. It should look like this.
And while you're loading all this, we have a couple of questions. So
go ahead.
For Syed Gul, how will we submit our homework and when is the due date for it?
Oh yeah, the due date, I'm not gonna put pressure on you for due dates. So you feel free to send it to me whenever you could. And let me put in the chat my email. That's my email. So send it to me by email. If you have questions, just let me know. Just shoot me an email and I'll work things out with you.
And then from an anonymous attendee, for those that don't have Microsoft, how would they be able to access the Excel sheet?
Ooh, that's a good question. You could use Google Sheets. You could use Google Sheets. And if you struggle getting it to work in Google Sheets, let me know and I'll help you fix it. That's good. Those are good questions. All right. If you're ready to roll, go ahead. But before you go into that, now that I share how that platform looks like, this is what you're gonna see. On the left-hand side, you see some information. Of course, the information is just giving you the welcoming to the space. Then you have three other tabs: Thermodynamics lab activities, material test activities, and the fluid lab activities. There are some videos related to Excel. If you're not fully familiar with Excel, I cannot encourage this to you anymore. You should get into Excel. It's very important. It'll be very important for your professional life. Whatever you do, by the way, even if you don't become an engineer, neither a scientist, please use Excel. Learn how to use Excel. It's very important for you.
Professor, it looks like we also have a couple of issues.
Yeah, go ahead.
Is there a login for Blackboard that they can use?
No,
Or
there is no need to log in. You're supposed
it
to.
looks like it's behind the ODU login wall.
It is, but you don't need to. Look at this. So I'm gonna look at this. If I paste the address right here, and I'm not logging in here, it goes straight to what? What the heck? This shouldn't be. It was working this morning. All right, give me a second. Let me figure things out. Try it again. Whoever asked that question, try again in another tab. What the? Let me see. Okay, this one works, but it is because I logged in on that browser. Let me do it again. Huh. I don't know what's going on, guys. I have no idea. Let me see if but it shouldn't be. It was working. It was really working this morning. Let me see. Let me close the tabs, and of course the sharing stop. Ay, ay, ay. This is weird. I tested out this morning. Oh, wow. I don't know what's going on. That should be the link. I'm so sorry for this. I'm so sorry for this. So let's do this. Whoever would like to get access to this, please send me an email to the email I told you. And for those of you that are watching this through YouTube, my email is O as in Orlando, then AYALA, which is my last name, Ayala, at odu.edu. Once again, O as in Orlando, then my last name, Ayala, AYALA, at odu.edu. I'm gonna try to fix this technical issue. So if you're interested in following this virtual lab, shoot me an email so I can reply to you with the correct link. Once again, I have no idea what goes on. I tested out this morning, but yes, it's giving me the same issues right now. It's asking me for a login, and it shouldn't. It should not ask me for a login. It should not. All right. I'll see what's going on. I'll see what's going on. Send me an email, and I'll give you the correct link later on. Are there any other questions?
We don't have any as of right now.
Okay. Well, if not, that's all I had for you. I hope to see you. Oh, by the way, you know what? Before I close this, let me. The problem is that I cannot log in. Okay, let me just show you what you were supposed to see, or what you will see once I fix the issue of login, the login issue. Okay, let me show you what it looks like. What is it that you're gonna be looking at? And that's this. So Tyler, what do you see? Do you see the welcome Reyes and Blackboard thing?
Yes, I can see that.
Okay, so this is what you're gonna be seeing once I fix the login issue. Once again, I don't have no idea what goes on, but you have three tabs: the information tab, which is the welcome page, then thermodynamics lab, materials testing lab, fluids lab, Excel videos, like I was saying before. So for the Excel videos, I highly recommend you to take a look at those videos if you don't know how to use Excel, because even if you don't go into the STEM field, Excel is extremely important nowadays. So as part of the other tabs, which are the thermodynamics, material testing, and the fluids lab, the one I want you to get into is fluids lab. My colleagues, Professor Nathan Lukey, will give a class next week on thermodynamics. And then my colleague, Nestor Escovales, will also talk to you about material testing lab. So these two are gonna be used in those classes. In my class, if you click for my class, fluid lab class, you see here's an intro for engineering technology. If anyone of you cares about to know the difference between engineering technology and engineering. And then the tab for forces due to static fluids. And you could see there is a technical background file, and there are few videos that you should watch one after the other. At the bottom is the lab activity. This will take you to a video that will take you through all the clicking, the virtual lab. So you'll be clicking in that apparatus I showed you before, and the Excel file that you're supposed to use to complete the task is right here. If you click on it, it's gonna get downloaded to your computer. Once again, I apologize for the technical issues. I'm gonna try to fix it today because I have another class this afternoon. And once I fix it, I'll send you an email. But then again, to avoid sending an email to all the people that registered for Reyes, shoot me an email to see that, to learn whether you're interested or not on getting into the lab. And with that said, I thank you so much for participating in this first class of fluid mechanics. I have another class in 3 weeks, in the last week of Reyes, and that'll be on the topic of forces as well. But the forces, it will be for moving fluids, because the equations when the fluid moves are different than when the fluid is static. So, and those are the forces that are very important for pumps, turbines, or devices of that nature. So with that said, thank you so much. It was a pleasure to teach you a little bit of what I know. And I hope you get engaged with the lab. I'm sorry for the technical issue, but shoot me an email so I can be in contact with you. All right. Thank you so much. Have a good day.
We had just one quick question.
All right.
I think we already covered it, but how will they submit homework?
Email. You send me an email to my email again. And once again, is O as in Orlando, AYALA@odu.edu. You could also search for me and you'll find my email. So search Orlando Ayala, all the universities, and you'll find my email. All right. Do we have any other question, Tyler?
No, we do not.
Okay, cool. Then we're adjourned. Thank you so much for listening. I'll see you next time. Hopefully I'll see you in 3 weeks. Enjoy Reyes. Bye, guys.